All right, good afternoon, and we're glad that everybody's back from their break. Session 14, set 14 sessions, plus a uh, poster session so far, so actually session 15 of the 3 days of the ISSR&D conference technical sessions. Well, this session today is Advanced Materials in Manufacturing, and we're going to have the session chair is Ryan Reeves. Ryan is with CASIS, the ISS National Lab, and we'll be bringing him up in a few minutes. The very first thing that we have to do is to show you the executive summaries. We have 5-minute summaries from each of our briefers, and they'll be bringing those in and playing those in a row. Then when they get done, we'll reintroduce Ryan and get you into the question and answer period. Go ahead and let's run up slides, please.
Hi, I'm Tracie Prater from NASA Marshall Space Flight Center. I'm going to talk today about the activities under NASA's In-Space Manufacturing Project. In-Space Manufacturing is a portfolio project which contains several different elements. Our overarching goal is to use the International Space Station as a test bed for evaluating manufacturing capabilities in a relevant environment. So we test technologies on ISS, and then they can be evolved for deployment on future platforms, primarily serving to support logistics reduction via point-of-use manufacturing. So the goal is to reduce the number of spares and orbital replacement units, which must be pre-positioned. These technologies also enhance crew safety by enabling adaptive response to unforeseen scenarios on a mission. So this is the ISS logistics model. This comes from an analysis by Bill Cirillo and NASA Langley, which illustrates the value proposition for in-space manufacturing technologies. So in longer duration and longer endurance missions, we will need to consider adjusting our mission paradigm to enable point-of-use manufacturing and repair to reduce logistics requirements. So on these farther out missions, we will not have ready cargo resupply options, and our stowage space will also be more constrained. So let's talk through each project element in more detail. Our on-demand manufacturing and metal components element is currently working with commercial partners to mature 2 different manufacturing processes for metals to potential ISS demonstrations. So one of these technologies under development is a bound metal deposition system from TechShot, which we call the Fabrication Laboratory or Fab Lab, and the other is a wire arc hybrid additive manufacturing system from Maiden Space known as Vulcan. Our recycling and reuse sub-project focuses on developing recycling technologies for ISS, recyclable packaging materials, which you can see in the right-hand image, and in-process monitoring capabilities to monitor and control the production of filament from waste materials on orbit. On-demand manufacturing of electronics is exploring different deposition techniques for 3D printing of electronics in a microgravity environment. So this multi-center NASA team, as well as university partners and a national manufacturing institute, work to develop custom inks for 3D printing of electronics. They're also developing sensors, which currently will be produced on the ground and then tested in a relevant environment on ISS. So these include sensors for environmental monitoring as well as crew health monitoring. And there is also a power and energy component to ODME. Our in-space manufacturing design database is the what we make of in-space manufacturing. So this catalog consists mostly of parts which are derived from heritage ISS systems. We also always want to have the capability to redesign a heritage part for an in-space manufacturing platform and have some activities related to establishing a methodology for that. We also have some in-situ resource utilization related work, in particular the Regis project with Maiden Space, which will demonstrate printing on ISS using a feedstock that consists of a polymer matrix and a regular simulant. So this is an important demonstration for one day using in-space manufacturing technologies on the lunar surface with indigenous materials. In-space manufacturing is a destination agnostic capability, so these technologies, once we've tested them using space station, can be deployed on other platforms beyond low Earth orbit. And really anywhere that you would be going and need to have a sustained presence, you would need these technologies as an enhancing capability. And so we're trying to do really exciting things and really transform the way we plan for and execute future missions. Thank you for listening to my talk.
Hello everyone, this is the executive briefing for the development of an in-situ geopolymer concrete for lunar infrastructure. To recap, the main motivation behind developing an in-situ lunar concrete is the Artemis program, where one day we plan to maintain a human presence on the moon, and concrete in the use of infrastructure is a feasible option. It has been shown that the 3D printing of concrete materials is feasible, and this work I'm doing to develop an in-situ lunar concrete not only has to have good strength and durability, but it must be able to be 3D printed as well. One of the first steps in this development of an in-situ geopolymer lunar concrete has been the microgravity investigation of cement solidification process, also known as MIX, where we send a variety of Earth-based cement components to the ISS pre-packaged in these burst pouches where they could be mixed by astronauts and allow for a one-to-one comparison of samples here. It is important to study these Earth-based components in microgravity, as the microstructural development of cement is a highly exothermic process. Microgravity minimizes transport phenomena like buoyancy and sedimentation and thermal solute convection, which are things that we expect and experience here on Earth. And this really leads to a diffusion-controlled hydration process in microgravity, and the resultant microstructure is quite different. The results from the MIX project have proved a few things worth noting, such as an increase in the amount of trapped air due to the lack of buoyancy in microgravity as shown in images on the left, as well as a reduction in bleeding in microgravity resulting in a porous network.
Weird. She must have been a very active question.
There are multiple supporting reasons for the creation of a geopolymer lunar concrete. It really stems from the goals to utilize as much in-situ lunar resources as possible. Traditional Portland cement concretes that we know and love here on Earth are not feasible on the moon, just given the low calcium content within lunar regolith. Also, the overall mass of a lunar regolith geopolymer concrete can be 90% regolith, where the remaining portion is the solution itself, and that is a combination of such as water and sodium silicate, which can theoretically be extracted from the regolith. Right now, the development of an in-situ lunar geopolymer concrete is in the preliminary groundwork stage, where I'm trying a variety of sodium silicate and sodium hydroxide combinations, as well as some potassium silicate solutions. These samples will be cured at different temperatures, some mimicking the daytime average lunar heat, as well as a vacuum environment will be used to see how that affects the compressive strength of these samples. The groundwork's really done to finalize mixture designs for an actual ISS flight experiment, and right now it's proposed that we use the same burst pouch design that the original MIX experiment did, as this has been proven to work and allow for a good, well-rounded microstructural development comparison. These were the preliminary compressive strength results for two different JSC-1A lunar simulant mixtures that I tried. These were sodium silicate solutions combined with sodium hydroxide at different molarities, specifically 10 molar and 14 molar. As we can see here in the graphs, that the 10 molar compressive strength for about 3 and 7 days was around 3,000 psi, where the 14 molar solution resulted in a compressive strength around 4,000 psi at both 3 and 7 days. Another important aspect of these geopolymer lunar concretes are their ability to withstand a harsh environment. To study this, we are going to pre-make some samples here on Earth that will be a part of the MISSY 15 flight experiment. These samples will be exposed outside the ISS for a minimum of 6 months, which will allow them to undergo exposure to a high vacuum environment, as well as extreme temperatures and solar radiation effects. After the samples return, a microstructural analysis will commence, comparing them to identical samples that were just left here in a laboratory environment. This will allow us to compare directly what kind of effects the exposure to an extreme environment has on the geopolymer lunar concrete. I would like to quickly acknowledge the people listed on this slide as well as the next one for making this work possible. Thank you all for your time and attention for this executive briefing on the development of an in-situ geopolymer concrete for lunar infrastructure.
Hello, and thank you for watching this introductory talk on microgravity characterization of molten metal oxides and synthesis of novel glasses. My name's Rick Weber. I'm the principal author of the talk and presenter. My colleagues Stephen Wilkie and collaborators Vrishank Menon and Sarah Schlossberg, all from MDI, Chris Benmore from Argonne National Lab, Mike Sansusi from NASA Marshall Space Flight Center, Bob Hires from University of Massachusetts Amherst, Jong-Yoon Lee from Iowa State University, Shinji Kohara from NIMS in Tsukuba, Japan, and Takahiko Ishikawa from JAXA in Japan. The goals of this work are to measure the thermophysical properties of molten and supercooled metal oxides and to synthesize glasses in low gravity, where transport properties are different, convection is suppressed, and sedimentation is suppressed, so one's looking at diffusion limited conditions. We're interested in measuring the density, expansion coefficient, viscosity, surface tension of the supercooled and liquids as they approach the glass. We're also interested in recovering glass samples so that we can analyze those and characterize those on the ground using X-ray and neutron diffraction and calorimetry. This work really relates to fragile liquids and developing novel glass products that can be useful in situ resource utilization and in development of functional glass products for commercial applications in optics and displays and other high-value areas. We will disseminate results through publications and presentations and attending conferences, for example, and through the NASA Physical Sciences Informatics System. And we'll use property data that's measured in the microgravity experiments in combination with atomic structure to model glass formation in these materials. The status is that the samples are made. Ground-based tests of flight worthiness have been completed. These include beam heating using the laser that will be used in the microgravity experiments. These experiments will actually be non-contact containerless experiments using the electrostatic levitation furnace developed by JAXA. And that non-contact technique allows deep supercooling of the liquid and often enables glass formation from these rather difficult materials. The first batch of samples was launched a couple of months ago, and the second batch of samples is being prepared for launch. The samples are mounted in carousels, and there's an example image of one of those in the below on the bottom left of the slide, and it holds 15 samples. So we'll have a total of around 60 samples for the whole project, maybe 70. The experiments will involve making measurements at 8 to 10 temperatures, and the schematic in the top right illustrates the temperature time sort of history that will be used. We have about 1 hour of orbit time between cutoffs in communication. So the goal would be to complete a sample in a 1 hour portion of orbit, or if necessary it can be cooled and reheated and the process completed in the second part of the second orbit. So each cycle will last maybe 8 to 10 temperatures, and these will be held for about a minute each as the drop is oscillated in the levitation system by adjusting the control parameters from the ground-based control room, and will be present in that control room in many cases, or tellying into it to contact and talk with the operators. Then the measurements of viscosity and surface tension will be made. The sample will then be reheated and melted by turning up the heating lasers again, and then free cooled, and during the free cooling the images will be used to measure the density. Since the samples are very close to perfect spheres in microgravity, then density measurements can be very accurate even with a single point of view camera, provided it has adequate spatial resolution. And in some cases the sample will cool to a glass, and in others it'll be recovered as a crystalline material. The ongoing work and plans are to fine-tune the experiment parameters for the ISS experiments. This involves using ground-based levitation facilities which, while they don't give the detailed control of sample of fluid motion, they do enable looking at the temperature-dependent effects on glass formation and cooling rates for glass formation. We're measuring the atomic structure of the new glasses made in ground-based tests, and we'll do the same thing for those made in the flight using high-energy X-ray and neutron diffraction, presenting and publishing results. So this work really underpins and impacts important aspects of in-situ resource utilization and commercial glass production. I would encourage you to attend the talk. It'll be presented as about a 15-minute sequence of slides. So I look forward to seeing you at the talk and addressing any of your questions. Thank you very much.
Hi everyone, my name is Nevin Brosius. I am a Ph.D. student in chemical engineering at the University of Florida. I'm going to present a collaboration work between UF, JAXA, and NASA Marshall Space Flight Center regarding the use of levitated molten droplets to measure surface tension. Levitation-based measurement and processing is really valuable because of its containerless nature. So we can measure thermophysical properties and phenomena that directly translate into really important engineering applications. There are several facilities that allow for levitation-based processing. Most notably in our project is the ESL at NASA Marshall Space Flight Center, and two identical pieces of equipment at JAXA in Tsukuba, Japan, and on the ISS on Kibo, where we will have an experiment slated sometime next year. Electrostatic levitation takes place by charging a solid metal sample and suspending it between a top and bottom electrode shown here in this animation. If we then superimpose an oscillatory electric field, we can cause, at first at low frequencies, solid body oscillation. And then as we increase the frequency up to its first resonant frequency, we can see this undulation which depends on physical parameters of the material. The relationship between the natural frequency of the droplet at which it would start to resonate most strongly is given here by this equation derived by Rayleigh. It's an inviscid equation. There are correction factors involved in this, but just to demonstrate the basic relationship, you see that the N represents the modal shape of deformation given by these two videos. Gamma is the surface tension, M is the mass, and F sub N is the frequency. The principle of our method is shown here, where we levitate a zirconium sample and melt it, and then subject it to a range of frequencies shown here, and record the amplitude of its maximum deformation as it's being forced. You can see a strong resonance point of 185 Hertz. You plug that into the equation shown on the previous slide, and you can back out its surface tension. Since our experiment is slated for ISS experimentation next year, it was important to verify the proof of concept on the Earth equipment. And so the way it works is we have the droplet resonating, and a laser shines a shadow onto the sensor. So we can perform a frequency sweep similar to what we did at NASA Marshall, and we obtain a resonance curve, and we can back out the natural frequency. Naturally, we wanted to look into extending the measurement of surface tension into higher order modes of oscillation. However, there's an issue with using the shadow area to quantify resonance, as is done with the area array. Here we have an animation showing mode 2 and mode 3 oscillations at the same amplitude, but the area is negligibly changed for mode 3. So this presents an issue. We now explain the projection method, which uses video data to quantify the resonance of mode 2 and mode 3 for the measurement of surface tension. We take the frame of the droplet, outline it, then convert it into polar coordinates, and perform a numerical integration. We then obtain a resonance curve, here for Inconel, obtained at NASA Marshall, and correlate that to its surface tension. Same process goes for mode 3, characterization. We take the frame of the droplet as it's oscillating, we outline it, and then convert it into polar coordinates and do a calculation and perform that over a series of forcing frequencies, and you can back out the surface tension, or the resonant frequency and then the surface tension. To summarize, resonance can be used in this fashion to measure surface tension in levitated liquid droplets. The area array used on the ISS and at JAXA can be used to quantify even normal modes of oscillation for the measurement of surface tension, but this cannot be done with odd modes of oscillation. They require high-speed video. Future work will involve using mode 2 and mode 4 resonance on the ISS. I'd like to acknowledge the funding agencies and our collaborators at JAXA and NASA Marshall Space Flight Center. And I also thank you very much for your attention.
All right, thank you to all the presenters who were able to come in and send their presentations in for this session. Again, our chair today is Ryan Reeves, Ph.D. from International Space Station, U.S. National Lab. He's the program director for advanced materials, so he's well qualified for managing this session. Now, we do have these 5 different presentations in this session. We'll leave it up for you for a moment so you can orient yourself with where we are. Actually, it's 4 presentations, isn't it? Should have read my script a little closer. And again, reminding everybody that's hearing this or seeing this on the net, please go down to the bottom of your screen and click the icon for Q&A. Type in your questions there. If you can't identify them to a presenter, please do so. Or if you have to identify them just to a presentation, just put the first word or 2 of the presentation's name in there. And I would encourage our presenters not to go into the Q&A tool and type in your answers. If you do that, then Ryan has to recall from memory what that question was so he can present it to the audience and re-ask you the same question. So I don't want to test his memory that badly. Ryan, go ahead and take it. It's yours.
All right. Well, thank you, Alan. And thank you all for joining this Advanced Materials and Manufacturing Technical session. If you have not done so already, I encourage you to view the full presentations that go into more detail than just these executive summary presentations that you just played. You can find those at the issconference.org website through the agenda. You can download the presentations and view at your leisure. And again, if you have any questions for the speakers, please submit those in the Q&A tab below and direct those to a specific panelist. Now it's my pleasure to introduce our panelists. We have Tracie Prater, a structural materials engineer from NASA Marshall Space Flight Center. We also have Peter Collins, a PhD graduate student from Penn State University. Next is Richard Weber, President of Materials Development Incorporated, or MDI. And finally, we have Nevin Brosius, a PhD student from University of Florida. So with that, let's pull up some of these questions. So first for Richard and Nevin. So Richard, I guess we'll let you go first. Are there any possibility to apply the experiment results for in-space manufacturing on ISS and future missions?
It's a good question. Thank you. We're looking at fragile liquids. We have quite a range of compositions based on metal oxides, alumina, silica, calcium oxide, magnesium oxide. So these are similar to the kinds of things that might be found in lunar regolith. Understanding the properties, the glass formation, particularly in the case of manufacturing things like bubble migration, for example, and the dynamics of the liquid, how it behaves and wets and melts, are important, and then the solidification processing. So I think as we move further into this project, there will be some important insights into that, particularly comparing the glass made in microgravity with glass on the ground, how those heat and mass transfer differences affect the product properties and structure.
All right, great. And Nevin, how does your work kind of apply to in-space manufacturing and future space missions?
Sure. Yeah. So our work is pretty fundamental in measuring surface tension, and so we have application in specifically metal additive manufacturing, where the surface tension and density, specifically as a function of temperature, is really important. And when you work in space operations, you have really high surface tension effects. So there is an effort to use materials that specifically have or are used in space operations. Like, for example, Inconel 625 is a super alloy, so it maintains its strength over up to near its melting point, and that's one of the alloys that we've tested and got surface tension values in our experimentation. So yeah, that's a huge focus in our research. So.
All right, thank you. Next question for Tracie. For metal 3D printing on the ISS, when will the testing phase end and the start of actual usage on board begin? Do you have a specific time frame you are aiming for?
Sure. So right now, the two systems that I talked about, Tech Talk Fabrication Laboratory and then Molten from Made in Space, are still in kind of the engineering prototype phase. Our project goal is to define metal demonstrations on orbit by 2024, which currently, space station in 2024 would be a little bit uncertain. So that's one reason for that kind of deadline. But I think the sooner we can demonstrate metal capability on orbit, that really expands kind of the use cases for in-space manufacturing and helps us better understand how we infuse these into missions beyond ISS as well.
Thank you. Next question for Peter. Could you talk a little bit more about the challenges of using moon regolith versus Earth regolith, and how the experiments in microgravity help you with just low gravity, quote unquote, on the moon?
Yeah, so right now we're going to use a series of different lunar regolith simulants. We have the JSC1A that I have left from previous experiments, and we're trying some from other companies as well. The important part of the lunar regolith that we're in the geopolymer systems, it's amorphous content. So the amorphous content of like the JSC1A is roughly 66% from our X-ray diffraction studies that we've done. And that's important for the polymerization process when you combine it with the sodium hydroxide and sodium silicate. The actual moon soil, I mean, I'm not exactly sure how that's going to play out and how it'll compare to the simulants, but we're trying to understand that through these simulants that we have here on Earth that are similar in oxide composition for sure. So hopefully it's transferable and applicable to the actual lunar regolith. Low gravity is important to these, just for the brief few things I said in the executive summary, such as the buoyancy and sedimentation effects, as well as the thermal pseudoconvection. As that becomes minimized, the polymerization process within a geopolymer is the same as cement, where it's an exothermic process. So the difference is you're not getting a variety of different crystalline phases that are forming. You're just forming an aluminosilicate chain network. So I don't think the effects that we saw in our initial cement studies are going to be quite as drastic as they are for these geopolymer ones, but it'll help us understand how the low gravity environment on the moon is more applicable to the microgravity environment from what we've seen so far. So the formation that forms in microgravity will be more transferable than studying these here on Earth.
Another question for Tracie. So as far as I know, forged and milled parts are stronger than 3D printed parts due to the melting the material to make the part layer by layer is like, all right, sorry, I'm not sure where that went, but in your experience, can you talk about the difference between 3D printed parts versus conventional? Do you expect a difference in the strength of those parts? And if so, how do you deal with that?
Yeah, so for the metals processes specifically that we're looking at, wire arc additive manufacturing is the welding drive process. So you're melting and resolidifying metal. So control of heat transfer, management of heat is very important to that process. And you would imagine, that would be different in a microgravity environment. So you'd expect some differences in the material. With bound metal deposition, so that's a two-step process. The first part of that is a forced extrusion process of metal particles that are bound up in a polymer, and then the polymer is debound and the remaining metal is sintered. So that sintering process may also be a little bit different in microgravity, but that's primarily the reason that we use space station kind of as the test bed, is to understand how those manufacturing processes operate differently in the microgravity environment, what aspects of the processes are impacted, and then ultimately do characterization of the ground specimens and the flight specimens as we've done with the previous polymer 3D printing activities and make that assessment. So it's really just understanding how the process and the material outcomes are different, or if they are different in microgravity, and then how we bound that and then design for it. In general, with 3D printing of metals, it's strongly dependent on the process, what the material outcomes are. But there are some processes where you can expect material properties for an optimized process that are better than cast, but not quite as good as raw material properties. So you really just have to understand the capabilities of your system and the material, and that informs how you design and use parts made with it.
All right, great, thank you. Going back to Peter, so you had talked about how in a microgravity environment, you end up with these voids because there's no density driving force to kind of drive the air pockets out or anything like that. And then you also end up with bleeding, with an absence of bleeding. So when you do this on the moon and you have a vacuum environment, does any of that change? Would you expect a different result than what you got, say, on the ISS due to the vacuum environment?
Yeah, so I'm not sure how it'll actually play out and work if it's ever done on the moon, right? The liquids don't want to stay in a liquid form in a high vacuum environment. So it'd likely have to be in some kind of pressurized environment where you would expect still to have issues with the amount of trapped air. We had another part of our initial mix experiment was using a centrifuge to mimic the gravity levels of like the moon and Mars to see how that played a role in the amount of trapped air that we have in our samples. And that's why I went back to say that the lunar environment or the lunar gravity is more similar to microgravity from our initial observations from our mixed samples, that the amount of trapped air is more similar at the lunar gravity than microgravity, because the force is still not enough to get the bubbles to rise out of the paste on their own, just due to the viscosity of how sticky the paste is in its original form. So like in a lunar environment, I'd expect those issues to still be present if you're in some kind of pressurized chamber where the liquid can remain in its liquid form until the concrete solidifies. Other than that, I wouldn't know how to address that issue if it wasn't in some kind of pressurized chamber where the liquid stays liquid.
Okay. Next question for Richard. So much of the point of your experiment, as I kind of understood it, was to gain the thermophysical property data. But can you talk a little bit about, would you expect there to be much of the way of a difference in the microstructure between this in microgravity?
I think the differences in the process relate entirely to heat and mass transfer. So there'll be changes in cooling rate, there'll be changes in the migration of material within the molten drop, and that of course depends also on the viscosity. And so we expect the glasses that are made in space will have a different fictive temperature. They'll be cooled at a different rate, so they'll relax differently. Structurally, it's unlikely that there'll be major changes on the atomic level, but in the bulk morphology, there could be changes from the core to the surface, for example, due to the different cooling rates and lack of convection in the liquid. So we might see a different strain profile, for example, in a piece of glass produced in low gravity from on the ground.
Okay, great, thank you. And then Nevin, question for you. So you demonstrated the n=2 and n=3 normal modes, and then you had kind of talked about at the end that you would look at n=4. So what are the limitations as you go to higher modes? Is there an absolute limit of what we can see? And does the information change as you go through modes, or is it just additional validation of your, say, n=2 mode?
So yeah, both are true, I guess. So the reason we're trying to look at higher order modes is to validate the surface tension measurement for the same sample. So we can go ahead and do this frequency sweep for n=2, and then do the frequency sweep for n=3. Now the challenge why we can't do like n=15 or something like that and just keep going is because that formula I showed, it increases very rapidly with n. So like for example, for zirconium n=2 could take for a 2 millimeter diameter sample could be about 180 hertz for n=2, and then n=3 is 360 around, and then n=4 would be 3 times n=2, and it just keeps increasing to very, very high frequencies. And the higher frequency that a droplet oscillates, the higher energy needed to destabilize it and cause resonance. And so that is really the issue with going to these higher order modes. You need to really give the droplets a strong amount of energy that in these systems, even though they're extremely professionally engineered and they're incredibly capable, struggle with causing the droplet to deform at these length scales. Now the EML is capable of exciting much lower energy excitations at higher order modes because they have very larger droplets, very much larger droplets, so the energy decreases. But yeah, the reason n=4 is being investigated, and I did not present data on it because it hasn't been shown yet. We're hoping to show that we can resonate mode 4, but it's because this area array needs an even mode to oscillate. And I think the benefit we would have from confirming the surface tension value with these higher order modes is huge, and it can provide a really nice benchmark measurement for surface tension. So hope that answered your question a little long.
Yeah, no, I think it does. Please continue to submit your questions down at the Q&A tab as we go through this, and kind of direct those to who you'd like to answer those. So the next question isn't directed at one person in particular, although I think it might be either Tracie or Richard. So you guys can kind of fight over who would like to answer it. But They ask about the possibility of fabricating silicon waveguides with integrated photonics, potentially I would assume in space. So is that something that we could do or anyone is looking to do?
I would probably need some more details on that to fully assess it. And if someone wants to reach out to me via email, I'm happy to do that. I can put you in touch with some of our on-demand manufacturing of electronics folks. But I know in the past they have looked at 3D printing of antennas and wireless communication and things like that. So I can't speak to whether that's specifically within their system capabilities currently, but feel free to send me a message about that and we can follow up.
Okay. So
I think that's a good point. Yeah, I agree. I think the dimensions of the waveguide are important. If one's talking about optical wavelengths, then the dimension precision would need to be very high, probably. So parameterizing that would be a good starting point.
okay. So going back to Tracie real quick. So when you look at recycling of polymers, have you looked at the degradation of those with increasing cycling times? And would you expect any change because it's done in microgravity in terms of how many cycles you might be able to get out of those?
Yeah, there have been some ground-based studies under our project with various companies to look at degradation of different polymers over multiple cycles, looking kind of at commercial off-the-shelf thermoplastics that are typically used in 3D printing systems, as well as we had a project on looking at packaging materials for space station and trying to develop a packaging material that can be processed into films and foams that then can also be recycled into filament feedstock. So a lot of the off-the-shelf thermoplastics don't fit well kind of within a recycling ecosystem. There are a couple that do, like PET, PETG, have good recyclability. But the material that was developed, it was from Cornerstone Research Group. They're a small business contractor materials design firm in Dayton, Ohio. So their material is thermally reversible. And so they demonstrated that they could process this into a film or a foam and pelletize it and extrude it into feedstock for 3D printing and do that over multiple cycles without significant degradation. So typically, with thermoplastics or packaging materials, you might have to incorporate additives to render them more processable over multiple cycles and ensure that they don't significantly degrade. Although I think it's some degradation, might be okay. That would just, you would just have to set limits on the life of a material and then define what it could be used for, given how many times it has been recycled.
Great, thank you. Next question for Peter. So for the ISS cement samples that were already conducted, those mix samples, how did the ISS samples compare to the ground samples in terms of density and the mechanical properties?
As far as density goes, it's really dependent upon, I guess, our initial mixture design as far as like the water to cement ratio, because at those like higher water to cement ratios that you saw in the executive briefing for like the mercury intrusion pore symmetry curve, the water has no reason to segregate from the paste. So you get that very porous network where everything's still interlocked. At more reasonable water to cement ratios of closer to like 0.3, 0.4 in that range that we actually use here on Earth, the effects aren't as noticeable. The porosity is very similar at these lower ratios when you don't get the segregation of the water. However, the microstructure is still, I would say, more porous, that you have a more uniform pore size, and it's not as variable across differing pores. Like there's a certain size that takes up the majority of the porosity that you get, versus where you get a kind of more of a well spread out thing here in terrestrial gravity, just given the way that the kinetics of the reaction transpire.
Okay, thank you. Next question for Richard. Let me pull it up here. So how does the levitation experiments on the ISS better enable measurements than, say, traditional terrestrial levitation?
There are a couple of factors that come into play. One of them actually is the very extreme difficulty of actually levitating the oxides on the ground in an ESL, although that can be done in some cases. But the ability to work in a low gravity environment where there's separating diffusion and convection allows a much more controlled drop. So the excitations will be more controlled and the measurements will be commensurately more precise because we're not dealing with extraneous forces so much. So it's really a matter of control. We have the control of nucleation and chemistry from the containerless, and then the control of fluid motion to get a quiescent drop that can then be studied in these really ideal conditions. And I think that's the real value.
Okay, and how would you compare this measurement in microgravity, say on the ISS, of thermophysical properties to any other way of measuring them here on Earth?
We want to measure the supercooled liquids, and that's why it becomes particularly challenging. In addition to that, the materials are fairly refractory, so the melting points are on the order of 1800 to 2000 centigrade, in some cases higher than that. So we have these multiple challenges together. And if one then wants to enter the supercooled region and look at how viscosity changes in the supercooled liquid as it approaches glass formation, that's very difficult, really. There's no way of doing that in a container. So ground-based methods are extremely limited, and the achieving the quiescent sample is really an important aspect, and that's really why one ends up with, this really is one of the toughest experiments. It's important to have the microgravity in it as well.
Okay, thank you. So Nevin, would you say with your stuff, was anything different in those answers? Is there anything you would add to kind of what Richard had to say on that?
Sure, yeah. So the main difference between, I guess, levitating and processing in microgravity and gravity is, the process of levitation is greatly facilitated because on Earth you're constantly fighting against gravity, and so for example, really dense metals like gold, platinum, iridium are borderline impossible to levitate. You need like a master magician basically to levitate some of these materials. And on the ISS, gold actually is one of the easiest metals to levitate and process. So whereas I don't think it's ever been processed fully on Earth. So there's certain metals that have characteristics like high density and low surface tension that make it very difficult to process really any other way, because you already have to go into these high temperature regimes to get them into a liquid state. Also, theoretically speaking, when you levitate a sphere in a gravitational field, if it's small enough, it will be closely spherical. But if its bond number is such that the gravitational effect within the sphere varies, you get the sagging, and the sagging effect causes the natural frequency to be different, causes the surface tension measurement to be inaccurate if you're going to do that on Earth. Whereas the very strength of the electric field and the density variation because of gravity in space is so minute, you can get essentially the closest you can get to a perfect sphere, which is huge when you're trying to get measurements to remarkable accuracy, I guess. So yeah, there's a huge incentive, I think, to process, in addition to what Dr. Weber said, there's a vast set of reasons that we process and characterize materials using this method.
Okay, thank you. So Tracie, for the Tech Shop Fab Lab, I know that they're doing bound metal deposition, but is it possible to do a different type of material, say like a, I don't know, a bound ceramic or something like that?
Sure. So in the phase A effort, which was a 2-year effort that just wrapped up, they worked with titanium 6-4. However, that system that they're using is a multi-material system. And when with a furnace, it would be compatible, I think, with ceramics. There's also a polymer head within that system for fused filament fabrication applications. So yeah, it would be versatile in terms of material.
Okay. Again, if anyone out there in the audience has questions, please submit those to the Q&A below, and we'll get those answered. Next question for Peter. So you're planning to do MISSE space exposure experiments. Do you know what orientation you're planning to expose those samples to? And which of the space elements or combination thereof do you expect to have the biggest effect on your samples?
Yeah, I think we proposed and got approval for the zenith phase, as that's the one most applicable to a lunar environment. I expect either the temperatures to be a big deal, but I assume more of the vacuum environment and the dehydration that'll cause of the samples and the micro cracking that'll happen to that. I assume the vacuum is going to be the largest challenge for any kind of concrete that is ever made.
So for Nevin, you were looking at a lot of different metals, and I think there was some maybe metal oxides in there as well. Can you give us a sense of the landscape for these thermophysical data sets? How much out there do we still need to do? Is there a database for that, or a body that kind of dictates what needs to be identified?
Sure. Well, that's not entirely within my scope. I'm not exactly sure of the attempts to put these surface tension measurements into a database. Now, I'm pretty sure that these measurements have been going on with levitation for at least 20 years, maybe even 30 years, going back to, I think, experiments at JPL. And there's been, again, from my impression, there's been some expressed interest from places like NIST to gather really high impact or important materials, surface tensions, viscosities, densities as a function of temperature using these methods. But yeah, in terms of like resources, any attempts to universalize some kind of database using this, I'm not super aware. It's not really my scope, but I know that there is expressed interest. I've seen it at the yearly ISS conference. There was a workshop recently and last summer as well, where there was a lot of expressed interest in surface tension measurement and at real high accuracy. There actually, the recent workshop, somebody said specifically the levitation based measurement of surface tension is very important for our processing. But yeah, that's all I know about that area.
Okay. And just to take this moment for a shameless plug, that you can find that workshop report that Nevin's talking about at ISSnationallab.org. It's a free download there, and you can see this year's and last year's reports. They're all available. Richard, kind of following that up, how do you see the thermophysical data landscape kind of in the glasses of there a lot that still needs to be mined in that area?
Yeah, I think there are a couple of aspects. I mean, the data that we measure specifically will go in the PSI database, and then that becomes available to other NASA researchers and I think essentially to the public at large. On a more sort of focused area on specific glasses, the Functional Glass Materials Manufacturing Innovation Council has been developing or working with large glass companies on the needs for modeling. And inputs and structure and properties are always one of the things that's lacking. So I think we come in at what you might call sort of TRL 1 or 2, fairly basic research where we're using prototypical materials that would feed into those projects where people are trying to model multi-component systems, which is a lot more challenging, of course. But if one measures these 2 or 3 component sort of axes of the multi-component phase diagram, you might say, that gives data that can be put together. So I think those models and the data will feed into models. And these benchmark data that are measured in low gravity will be very useful for pinning down values for the materials that we actually measure and also validating the techniques and also perhaps validating ground-based techniques as well in some ways.
Okay, thank you. So just a couple minutes left. This one wasn't necessarily directed to a particular person. So Tracie, I'm going to make you the unfortunate, one to field this. Is there a way to scale down or to do, they phrase it as a low scale microgravity environment. Is there any way to simulate it on Earth or to do any sort of gravity averaging kinds of experiments here?
The challenge for manufacturing processes and evaluating microgravity effects on the process on Earth is just the time constant that you would get with a parabolic flight. Right? You're looking at about 30 seconds of microgravity. I think with New Shepard, Blue Origin, you get about 4.5 minutes. And then with drop towers, you just get a few seconds. So while it's certainly valuable to use those to evaluate, what you can about a process and material outcomes and how the system might function, you really do need that long duration microgravity time constant of space station. And we kind of view space station as kind of the bounding environment, right? We obviously want to transition these technologies to the lunar surface, eventually the Martian surface, which are fractional G's and not 0G. But we kind of view if you can operate on ISS in that that long duration microgravity time constant, then it should also work on the lunar surface or on the Martian surface. I hope that answers the question. I'm not sure I completely understood what was being asked.
I didn't necessarily either. That's why I kind of saved it for the end here. But thanks for answering that. So just 1 or 2 more questions. Peter, the way in which you had designed the experiment to be operating on the ISS, where you had these pouches and you were going to puncture them and have the astronaut crew kind of roll them and knead them. How did you look at the mixing process and how that might compare? How well dispersed things might have been?
Yeah, we did some ground-based studies beforehand when we were going through all the iterations of how we wanted to actually conduct the ISS flight experiment. And we did numerous mixes in the pouch and then compared them to ones that are done in a typical like benchtop mixer for concrete samples, and looked at the microstructure and see if there's any noticeable issues with the dispersant and the phase formations. And we found that mixing them for at least a couple minutes with your hand as well as a little rubber spatula the astronauts got was more than enough to get an even microstructure that you'd expect as here on Earth through like the benchtop mixers. There are no issues, I guess, necessarily in the pouches as long as they're well mixed with the hands and the rubber spatula.
All right, Ryan, Thank you very much for running this session. In my senior year in college, I did a materials science project for my senior project. And this is all so much beyond that. I know nothing about materials compared to any of this. So thank you very much.
Well, and thank you all to all of the panelists. It was a great panel, and I enjoyed it. So thank you.
Okay, thank you, panelists. Now, warning to my AAS friends, I'm going off script. So just beware, guys. So I'd like to ask Sarah Robertson to pull herself up on camera, please. Sarah, would you do that, please? And also, Sarah, we're waiting. Yeah. She was busy
She's working on
managing the conference. Yes, she is. Sarah is our communications coordinator, and as such, she manages all of the emails and things that we put out about this conference and all of our other conferences. And she also does the majority of the graphics that you see coming out of the conference management world, which you might not think is very much, but there's about 40 different graphics a day that she had to create. So Sarah just came to us a little while ago, and she's doing a great job helping us manage the conferences. Next, I'd like to introduce Patrick Ruin. And Patrick there is our events manager. And what he's done with us on this conference is help us adjust to the platform. You can't adjust platforms very well to what you want to do, so you have to adjust what you're going to do to the platform. So Patrick has done a great job at that, and has made us actually look reasonably professional at this, or at least we don't bungle too much. And then Patrick and Sarah did a few extra things on this conference which are kind of invisible. Uh, they managed 85 individual tech checks with different presenters and folks in the conference, and 3 major group tech checks to make sure that everybody could communicate and be able to participate in the conference. And they did find a number of really serious problems that if we had waited till run day to do, we would not have been able to have a couple of chairs or some of the presenters in the conference, because we would not have had time to troubleshoot that. Also, a somewhat bigger job they did was that they managed 113 5-minute briefings, downloading them, putting them in the right place, and running them in the conference. So just think of if you had to manage 113 5-minute briefings in 4 different formats. So they did a great job on that. And now I'd like Jim Way to come in. Jim is our executive director for the AAS, and he manages Patrick and Sarah, but he's also managed the development of this conference and putting together all these technical sessions. He's also been our real-time director, so that he could come in and take care of making sure we put everything together. Doing that, he had to have a couple of headsets, a couple of comm loops, 3 computers, watching everything that's going on as almost the same thing you'd see a director on television doing. So if I had a way to go off and have everybody give these guys a hand, I would do it, but I can't do that. If you want to send a little chat in to say, thank you, Jim and Patrick and Sarah, I'd appreciate it, but I'll give you a clap myself. Thank you all very much.
Big thanks to Patrick and Sarah. Huge thanks.
And now, we get to have a break. They get to have their potty break. I took away some of their potty break. So what we're going to do is take a break until 17:15 Universal Time or 1:15 Eastern Time, when we'll come back with Earth observation and viewing. And one of the things Jim Way is doing, he is also sharing co-MCing of this for us. You'll be amazed why you really need 2 MCs, but it's really important. And Jim has picked that job up also. So thank you, Jim. And everybody else come back at 1:15.